Hello and welcome to this new video from the clustering playlist. There's another video that I covered recently, which was again about this famous problem statement mixed data types clustering using Gauss distance. Today I'm going to emphasize another famous method that is used widely for clustering data sets that have got multiple kinds of data types like ordinal, numerical, categorical, all those kinds of things, Okay, so let's start. First thing, again, we come back to the pain point, mixed data types. Same old shit, k-means, k-modes cannot handle mixed data types, the famous algorithms. So we need to look out for some specific algorithms that can deal with mixed data types for clustering algorithms. Why I'm specifying or I'm emphasizing a lot on this problem statement? It's because majority of the data sets that you're gonna find while working with data science projects is going to have a lot of different kinds of data types in it. So whenever I'm appearing in an interview and I showcase a project in which I did some clustering analysis, the first question that they're gonna ask me if they are a student of clustering is that how was your data set? How did you handle mixed data types? Because this is what they're looking for, right? Whenever you're dealing with real world data, 99% of data sets are going to have mixed data types in them, and it is very important to know and understand deeply what are the different options in our arsenal that we can use to deal with a problem statement like this. So k-means algorithm, which is the most popular algorithm. By the way, I am assuming that you have understanding of k-means algorithm and k-modes algorithm. If you don't have it, still I'm going to give a small sneak peek into it. But if you want me to create a detailed video on these basic forms of clustering, just put it down in the comments. So k-means clustering uses the Euclidean distance metric and k-modes uses the Hamming distance metric. The Euclidean distance metric is well suited for continuous numerical variables, and the Hamming distance is well suited for categorical variables. But when we have a data set that has both of these kinds of variables as well as some ordinal data, we need to look out for some different kind of distance metric. In the last video we saw Gauss distance. In this video we're going to see how we work with this problem statement using the k-prototypes algorithm. So k-prototypes clustering, let me give you an introduction of what it is all about. It is based on the idea of utilizing the good things about the k-means and the k-modes clustering algorithm to devise a new kind of a distance metric, a new kind of a clustering algorithm, where we can treat the numerical variables using Euclidean distance like we used to do in k-means, and treat the categorical variables using the Hamming distance as we used to do in k-modes, and then combine both of these distance metrics, distance metrics, my bad, and then we can get an idea of how two data points differ from each other in a quantitative manner by utilizing a combination of these two distances, even if they consider categorical as well as numerical variables. So the best part about it is that k-prototypes clustering is more suited for large data sets as compared to Gauss distance, and k-prototypes clustering has more flexibility in terms of initialization points and in terms of the distance metric that we are going to use, where we can introduce a hyperparameter, as I've said here. So you're gonna see all of that in the hands-on part of this session. But yeah, it's more flexible, it's more scalable, and it is from a superficial point of view, a combination of k-means and k-modes. Cool. So as I'm using the words k-means and k-modes a lot, and using the words Euclidean and Hamming distance a lot, let's take a sneak peek into Euclidean and Hamming distances, so that you can get an idea of k-means, k-modes, as well as a kind of a revision of Euclidean and Hamming distances. So Euclidean distance is the good old distance metric that we use to find the straight line distance between 2 points in a multidimensional space. And as shown here is the Cartesian space, which is the 2-dimensional Cartesian space. And it's just a simple kind of a hypotenuse kind of a formula, where if there is a point over here, which is, say that this point over here is, let me just a second, I need a pen. Say that this point over here is 1, 2. Okay, yeah, this one looks taller than usual. And then here we have a point as 4, 6. So the Euclidean distance between these 2 points is gonna be 6 minus 2 whole square plus 4 minus 1 whole square, the entire thing under square root. It is gonna be 4 square plus 3 square, that is 16 plus 9 is gonna be 25 under square root. So the distance is gonna be 5, as you can see over here. So this is the usual Euclidean distance. I'm sure you guys must be knowing about it. Now let's take a look at Hamming distance. Hamming distance is a very simple kind of a distance which is devised to find the dissimilarity between 2 data points which have only categorical variables. Okay, now the Hamming distance about which I'm going to talk to you is going to be in the context of clustering data sets. Okay, but Hamming distance also has a lot of applications in finding dissimilarities between strings and all those kinds of things. That's a different kind of an application of Hamming distance. But over here, as we can see, use case that there are 3 rows with us. ID is the primary key. Okay, let me just where did this thing go? Let me just get the laser pointer. Yeah. So there are 3 rows. A, B, C is the primary key over here, identifier. And we can see that there are just 3 categorical columns: gender, owns house, married. And 1 means yes, probably. And in case of gender, it means male, and 0 means female or whatever. In owns house, 1 means yes, he owns a house or she owns a house and stuff like that. Okay. So how do we find a distance between these 2? Say we need to find a distance between A and B. Here the Euclidean distance won't make any sense because these are encoded values, right? These are not continuous numerical values. And even if you want to explain that shit, how are you gonna say that, okay, the distance between male and female is 1? Okay, those 2 are not distant from each other. That what you can say is male is kind of different from female. That's what it's supposed to mean, right? So there's no using Euclidean distance or any kind of generic Cartesian space-based distances when dealing with categorical variables. You might have seen the same thing, similar kind of a thing, in the Gauss distance video. So here, what we do with Hamming distance is that we kind of add up the number of columns where the values for row A and row B differ from each other. So in the first column, gender, A and B have different values, so we say 1 over here. In the second column, the A and B rows have the same value, 1 and 1, so we count it as 0 because they are similar. And then again it's different for the third column, so we again take it as 1. So whenever the values for a particular data point is different, for two data points are different in a particular column, we consider that as 1. And if it's similar, we count it as 0. It basically means that it's identical, right? So you can see the simple formula over here where we are using this function where this thing is equals to 1 if ai is not equals to bi, and 0 otherwise. If they are equal, we consider it as 0. So you can see the Hamming distance between data points a and b is basically 2. And if you count the Hamming distance between a and a, it will be 0, which is what we want it to do, right? Because it's the same data point. So this is kind of a high level view of Euclidean distance and Hamming distance. This is what's being used to handle the categorical columns. This is what's being used to handle the numerical columns in K prototypes clustering. Move forward. So again, the most important part, the theoretical part, we need to get to this before we go to the full-on hands-on session with Python. Because guys, as per my experience, in data science, there is one very famous quote, okay? There is no free lunch. You have to work for it. You have to go through the theory, the mathematics of it to understand the algorithms. You can't just rely on the different libraries and think of every single algorithm as a black box. So always let's spend, like always, you must have seen that in almost all of my videos, we spend some time in learning about the why, how part, the back-end part of every single concept, right? So what's the intuition? What's the entire idea of K prototypes? Okay. So as I said, for numerical, K-means used to do a good job at clustering numerical data, right? Using the Euclidean distance. So we are using Euclidean distance for numerical columns, which is this formula. This formula is the same as what we had in the previous slide. So this is basically Euclidean distance. Here you can see we have the distance between xi and ck, which basically means the ith data point and the kth cluster is given by this. If you know k-means, then what we try to minimize is the within cluster sum of squares. So the distance between each data point and its respective cluster, we get that by Euclidean distance, and then we just update the centroid, and through this recursive approach we look forward to convergence, where we no longer need to update the centroid. And how are the centroids found? By taking the mean of all the data points, right? So here average in here, simple kind of a thing, kind of a note point. A k-means operates through an iterative process that minimizes the distance between data points and the respective cluster centroids, followed by the reassignment of the centroids based on the updated clusters. So this is how the numerical part is handled in k-means. Now, coming to the categorical part, we use k-modes clustering when dealing only with categorical data, and k-modes does a good job at clustering categorical data based on Hamming distance. And here we calculate the distance between ith data point and kth cluster. This is basically the kth cluster centroid, okay, using the Hamming distance, like we saw in the previous slide. And then what we do is that we update the centroid by taking the mode of the data points which are assigned to that particular cluster. It'll all make sense as we move forward, and we take a practical look into all of this, okay? So don't worry about it if you don't understand a particular thing over here, okay? Consider it as an overview. We are diving deeper and deeper slowly, okay? So again, k-modes operates through an iterative process that minimizes the dissimilarity between data points and the respective cluster modes, followed by the reassignment of the modes based on the updated cluster. So in numerical, in k-means, the cluster centroids are updated by taking mean of them because those are numerical values. But in k-modes, the new cluster centroids are assigned by using modes of the data points, because here the mean wouldn't make sense, right? Now, ordinal By the way, when we are talking of K prototypes, usually people don't talk about ordinal columns because it's kind of considered as a combination of K means and K modes. But guess what? We can handle ordinal columns as well. So I've included it over here. For an ordinal column, the values are simply treated as ranks. We ordinal encode them. So if we have three values, say high school, bachelor's, and master's, we just encode them as 0, 1, and 2. So now we have ranks for them. Now after encoding them, we simply consider them as a numerical column, okay? And we do the same shit that we used to do with the numerical columns. So we used to do this in Gauss distance as well, if you remember. So for an ordinal column, the values are treated as ranks. And then this similarity between data points I and j is calculated similar to numerical column by just normalizing the difference between them. So it is one of the strategies, as I said, it is one of the strategies. You can, do more stuff with ordinal columns if you want, if you have some kind of an issues. But yeah, this is a kind of a very generic strategy of dealing with ordinal columns, that encode them, then treat them as numerical ranks, okay? Now, moving on to the practical understanding. Here we are going to see a very small use case where we will try to dive deep into how K prototypes works. So here I have this very small data set with age and income being the numerical column. Gender and owns house are the categorical columns. We don't have an ordinal column over here, but we will be dealing with one in the hands-on session, so don't worry about it, okay? So I have divided the entire process of how K prototypes works into steps, okay? So first step is random initialization of cluster centroids. So we go into the data set and we pick whatever value we assign. So you know that in K prototypes, K means, K modes, a significant quality of these kind of clustering algorithms is that we provide a certain K value beforehand. So we can provide the K equals 2 over here. So that would mean that we are telling the model to assume that there exists 2 clusters in our data and work accordingly. And then we kind of iterate through different number of clusters to see which particular value of K is giving us the lowest cost function value, and then we select that. That's the basic thing, okay? So here, say that I assigned K the value 2. So the first step will be random initialization of cluster centroids, which basically means that my algorithm will randomly pick 2 data points from this data set. This data set is literally 3 rows only. So say that it picked the 2 data points from here, any 2 data points, okay? And though it will consider those 2 data points as the cluster centroids, okay? So I think here the age is not matching, but you can consider simply that, okay, this thing, 25 and 45, any 2 can be considered as the cluster centroids, okay? Say that these 2 are rows. Don't get confused by the age over here. I think I just made a mismatch, but yeah, it's fine. It ought to be 2 rows from this data set, okay? So it will randomly consider 2 particular data points as the cluster centroids. And the question is, what you should ask is, why are we randomly initializing them? Is there some other method of doing this? Because random initialization means that we are starting from random data points and then we are slowly converging towards the 2 most optimal data points for cluster centroids, right? So the answer is there are other strategies, and we will be looking at one in the hands-on session part where we won't be initializing the cluster centroids randomly, okay? Then what we do is, second step, we find the distance between each data point and the centroids. So these are the 2 centroids. So what we will do is we will find the distance between each centroid and each data point. So for example, we find the distance between the first row and both of these centroids, and say that the distance between row A, I'm calling it row A because A is the unique identifier over here. Distance between row A is with cluster 1 is higher as compared to cluster 2, then it will get assigned cluster 2. Then I will say, the algorithm will say that okay, row A belongs to cluster 2 because it is closer to cluster 2's centroid. That's how it works. So here we will simply do this calculation. But the thing is, how do we combine the calculations for the categorical columns and the numerical columns? So here, what K prototype does is, we calculate the distance between the cluster centroids and the data points separately for the numerical columns. So here I'll be calculating the distance between the cluster 1 centroid and row A separately for the numerical columns, age and income, and then separately for the categorical columns, gender, owns house. So here you can see that I've got a numerical part of this distance, and I've got a categorical part of this distance. This distance is calculated by the Euclidean distance. This distance is calculated by the Hamming distance. We combine them by simply adding them up, and we also introduce this hyperparameter gamma, which we can assign any kind of value based on what kind of importance we want to give to the categorical columns. Okay, so by default we keep it as 1, and I'll show you how you can assign gamma in a hands-on session. So here I've shown a sample distance calculation between data point A and centroids, these two. Don't worry if the values don't match, okay? So you can see that for the numerical part we did a Euclidean distance calculation, and for the categorical part we did a Hamming distance calculation. So for cluster centroid 1 and row A, gender is male, owns house is yes, so the Hamming distance between cluster 1 centroid and row A will be 0 definitely, and the Hamming distance between cluster 2 centroid and A will be 2, as male is different from female, and owns house yes, owns house no. So we'll have 1 plus 1 as you can see here. So we got a distance. Then we can understand from over here that okay, our data point is closer to cluster 1. So I can assign that my data point A belongs to cluster 1. So the third step is assign each data point to the nearest cluster centroid. So here A is assigned to cluster 1. Now one important thing, guys. You see the scale of these two values? The distance between the numerical columns is in thousands of scale, like even tens of thousands. And the scale of the distance between categorical columns is in the scale of 1 or 2, I mean in kind of binary scale. Therefore, you get an intuition, you get an idea that we must always scale our values when dealing with K prototypes clustering. Because if we don't, the distances, seriously, the categorical columns distance will always be kind of overshadowed by the distance between numerical columns, because this is always going to be in the binary format, as you know about Hamming distance, right? It will always be in zeros and ones. So there's that idea. So when we do it in the hands-on session, we will take care of the scaling part, definitely. So now we have assigned each data point to the nearest cluster centroid. Now let's see what are the subsequent steps. So as you can see, based on the distance that I formulated, I assign cluster 1 to A, cluster 2 to B, and cluster 2 to C. Now the fourth step is update the centroids based on the cluster means. Now the word means over here is kind of misleading, because whenever we are updating the centroids, it means that the new cluster centroid for cluster 2 will be the mean of all the data points that belong to cluster 2, and the new cluster centroid for cluster 1 will be the mean of all the data points that belong to the cluster 1. Over here only 1 point belongs, so it doesn't matter, the centroid will stay the row A only. Cool. So how do we find cluster centroids now? How do we update them? Again, we treat numerical columns and categorical columns separately. For the numerical columns, we just find the mean of the existing data points because those are Euclidean distances. We can take a mean of them. In categorical columns, we take the mode of the categorical columns in the cluster. So, over here, Owen's house has two separate values. I'm trying to update the cluster centroid for cluster 2. Simply, I will know that the cluster centroid should have an age which is mean of these 2 points that belong to cluster 2. So, mean of 35 and 40. 35 and 45, which is 40, as you can see here. And then the mean of income, which is 65,000, as you can see here. And now for gender and Owen's house, which are the categorical columns, we take the mode. So as you can see that in cluster 2, female is occurring the max number of times, male is non-existent. So obviously the centroid's gender's value will be female. In case of Owen's house, it is yes and no, equal values. So we can't really get a mode. So we can just assign yes or no depending on what it picks. That doesn't really matter now, okay? But obviously, this is a very small data set and we won't deal with such an issue in real world data sets, right? Cool. Now we get this new centroids and then again we calculate the distances. Again we reassign clusters to the data points. Again we get a centroid just the way we used to do in k-means and k-modes until and unless our algorithm converges and the updation of the cluster centroids doesn't really make a change. The cluster centroids don't change on updating them. So that's the entire overview of K prototypes, the theoretical part, okay? Now, very important. This is a personal thing that I'm telling you from my experience. Whenever you are learning any machine learning algorithm, okay, there must always be a section called as considerations, limitations, or pitfalls associated with this particular ML model. You should always focus on that because that's what differentiates a normal ML expert from a expert ML expert, okay? They know when to do what. So here there are some considerations. There are some limitations of K prototypes clustering that you must have in your mind when using this algorithm in real world scenarios. First is that you saw that K prototypes is really sensitive to scaling. If we don't scale our values, we are going to get in big trouble. So first thing, sensitive to scaling, definitely. Second, highly sparse data with a lot of dimensions can cause the algorithm to struggle due to the curse of dimensionality. Now, if you don't know about the curse of dimensionality, I highly recommend you to read it. I might also cover this thing in later sessions, when I'll try to create a video on PCA, UMAP, stuff like that. But what it basically says is that when your data set has a lot of columns, when the dimensionality is really high, then the distance between any two data point is very large. And when they are equally large, the relative difference between them doesn't really make sense, okay? So our algorithm, K prototypes, K means, all of these algorithms which are based around distance metrics, they kind of fail to observe real patterns and they start picking up on noise. So we need to take care of this, okay? How can we take care of this? That's an advanced thing. We can take a look at it later if I try to create a real world project or something. But yeah, that's a limitation again. Third is categorical data with high cardinality like cities and pin codes, stuff like that. So our K prototypes can handle categorical data, but it will face problems when dealing with high cardinality. High cardinality basically means a lot of unique values in our categorical column. Just imagine if we have a categorical column called cities, where we have literally hundreds of cities, hundreds of unique values. As our algorithm is based around finding the Hamming distance and finding the differences and finding the modes, it will obviously face a lot of issues when dealing with a dataset that has so many categories, as we won't be able to find a meaningful mode or a meaningful Hamming distance a lot of times. So how can we deal with this? We can maybe categorize each city, each pin code in this particular case, but maybe we might get rid of some some columns with high cardinality while applying this algorithm. Fourth is another important issue that happens a lot in real world scenarios. Imbalanced categories can cause an issue in centroid calculation. So think of a categorical column where we have a lot of females and very few males, say 10 males and 100 females. So that categorical column is immensely biased, right? What that would mean is, whenever we are trying to update a cluster centroid, we are doing it on the basis of modes. And every time you are going to get female as a value for the mode, because it just occurs a lot many times as compared to the male category. So that makes your algorithm very biased, right? Because that's not a pattern, that's not picking a pattern. That is just a flaw in the data set. So you need to be careful about that. And the fifth one assumes a spherical clusters. So the k-means algorithm, the k-prototypes algorithm, all of these algorithms are based around an assumption of spherical clusters. So whenever we are dealing with elongated clusters, you might want to read about this, by the way. If you don't know about what spherical clusters are, just go and read about it. So these models are not designed for dealing with spherical clusters, non-spherical clusters, okay, like elongated clusters maybe. So there's a problem if you have that kind of a pattern in your data. For dealing with non-spherical clusters, we use Gaussian mixed model that I'll cover in a later video. If you show interest in that, that's a beautiful concept. We use agglomerative hierarchical clustering, all those things, okay. Local minima convergence issues. Now this is a very common issue with k-means, k-modes, because we are, as you saw, that we are randomly initializing the cluster centroids, and it is very likely that we might converge on a local minima. Our algorithm will converge on a local minima, which is not the most optimal centroid position. So how can we, this can be remedied by just randomly initializing centroids in like 10 different positions, like we used to do in k-means plus algorithm. So we have a pretty good idea, pretty detailed idea of the algorithm now. Now we are ready and warmed up to jump into the coding part of it, the hands-on session part of it. Hope you enjoy it. Hey, stop. I hope this video is being instrumental to you. Just wanted to let you know that you can support me by buying me a coffee in the link given below. Your support would let me know that I'm on the right track and would motivate me heavily to create high quality content for you and the community. Get going. Alright guys, so let's begin with the hands-on part, okay? So here are some pretty common libraries that I have installed over here. I will attach the link to this Google Colab notebook, and it'll be pretty easy to just execute all of this one by one. And I have the k-modes library over here. The k-modes library is the one through which we can access the k-prototypes class, okay? So cool, let's begin. So here, as usual, I have preferred to go with a dummy data set. Two reasons for that. One, the data set is small and understandable, okay? So it's very learning friendly, okay? You can just look at this data set, understand every bit of it, how the clusters are looking like, and you can completely grasp the entire concept through this data set so that you can apply the concept to real world data sets. By the way, if you want me to create a proper real world project of clustering or anything, just ping me in the comment section. But this is a tutorial video, this is learning video, detailed guide sort of. So yeah, here we are. So this dummy dataset is not just dummy dataset, because this dummy dataset has been designed. I have got it generated through AI so that I can get some meaningful clusters out of them. Okay, so cool. And I have imported the min-max scalar, label encoder, ordinal encoder, the pre-processing modules from the sklearn.preprocessing, and we'll be using all of this. Cool. So I imported all of this, and this is how my dummy dataset looks like. I think there are around 20 to 30 rows in this. Age, income, as you can see, are numerical columns. Gender is a categorical column. Loyalty level is an ordinal column, and preferred product again is a categorical column. The loyalty level has 3 levels, so I'll be using that to ordinal encode it using the ordinal encoder class from sklearn. And I have defined the categories as low, medium, high. So I want low to be attached to the value 0, medium 1, and high to be 2. So I encoded it, the loyalty level column, and here we have the encoded one. And as soon as we encode the ordinal column, we can ensure that we'll be treating it as a numerical column in K prototypes. Okay. Second, I told you that whenever dealing with K-means or K prototypes, we always need to scale the numerical columns, or else we'll be facing the problem as you saw in these slides. The distances will be skewed or very biased towards the numerical columns, or whatever the situation is. And why are we using the min-max scalar? Why not the standard scalar, if you know about the standard scaling? Because min-max scalar scales all the numerical values to 0 and 1, which is very terrific for comparing it against the categorical values or the ordinal values, because we know that categorical columns values lie between 0 and 1, right? So we want numerical columns to also be between 0 and 1, and not between -1 and 1. That would be difficult to interpret because we are dealing with numerical and categorical columns together. So I scaled the numerical columns using the min-max scalar over here, the age and income column, and as you can see, I've got the scaled values over here. Then I need to get started with the clustering part. Before getting started with the clustering, I'll be using the K-modes library as I showed you here. And K-modes library expects us to provide it the data set in a particular format, which is a NumPy array, and not in a data frame format. So first I convert the data into an array, and I need to specify the categorical features index over here. So I basically need to tell the K prototypes class that these are the index in which you'll find the categorical features. So over here the categorical features are at 0, 1, 2 second index, and then 3, 4 fourth index. So I specified that. Now one thing, if you didn't get this question, you must get it, that my ordinal encoded column is in a scale of 0 to 2, while my numerical columns and categorical columns are in a scale of 0 to 1. So should I scale that as well? The answer is you might do that, but here it is not advisable to do so, because anyways the scale is not very distorted. I mean, it's just from 0 to 2, as compared to 0 to 1. But if your ordinal column scale is large, so for example if you have a lot of ranks, then you need to consider some other strategies to tackle that, because then the scale of those values will impact your clustering algorithm's performance. Okay, so now we do the normal stuff. We find the optimal number of clusters for our dataset, because in k-means clustering, I'm sorry, in k-prototypes clustering, just like in k-means or k-modes clustering, we need to specify the number of clusters that we want to form in our dataset. So by default, we don't know how many clusters we should have in our dataset. So we do the normal stuff, which is train our model for different values of k, and then check out the value of a cost function, which is within cluster sum of squares in k-means. Over here, we have a different kind of a cost function. I'll show you what it is. So here I have trained the values for 2 clusters, 3 clusters, k equals 2, k equals 3, using the k prototypes class. You must be thinking, man, why didn't you do it in a for loop? And the reason is that for some reason it was showing up an error. I just wanted to save time and I didn't tackle it over there. But yeah, maybe there was some issue, so I just did it in a one by one kind of format. Okay. And I wanted you to pay attention to a few things over here. There are 2 parameters currently, number of clusters, which I specified equals 2 over here because I'm training it for k equals 2, and I have provided an init parameter which is Huang. Now what is Huang? Okay, so you remember I told you about the first step in k prototypes algorithm is to randomly initialize or randomly assign k number of points as the cluster centroids, right? And I told you that it might not be the best approach to just randomly assign k points as cluster centroids, and we need to have some kind of a logic if we want the model to converge quickly and accurately. So Huang is the guy who basically published a paper in 1997 regarding the k prototypes, and he was kind of the guy who found k prototypes, or who proposed the fundamental k prototypes approach back in 1997. So his idea is that he has a strategy for initializing centroids. It basically says, I'm not going into detail into that, but what it basically says is that when you have a data point, you select the first cluster centroid randomly, and then you take the pairwise distance of every single data point from that assigned cluster centroid, and then you assign the farthest point from the current cluster centroid to be the next cluster centroid, and then you do that again. So basically it's ensuring that the 2 cluster centroids which we are assigning initially are 2 points which are at extreme distances from each other, so that our algorithm converges quickly. Okay, I'll share with you a research paper on this towards the end of this session, so you can read about it. So yeah, it's pretty basic. We just initialize the k prototypes with the init Huang over here, and if I wanted to go with random initialization of centroids, I would just write init equals random over here instead of Huang, or that is the what we call the default if we don't assign anything in init. So we do it for all the k values that we have considered over here, 2, 3, 4, 5, 6, and I am appending the cost function value for each of these k values to the cost list, so that we can analyze each of them, and then we can use the elbow method on it. You must be knowing the elbow method from the k-means. Okay, so we know that in k-means the cost function is the within cluster sum of squares, which basically means that k-means attempts to minimize the distance of each data point from its cluster centroid. And here our cost function, because we are dealing with a more diverse metric, our cost function is basically the sum of all dissimilarities within that cluster, which basically means we have that expression, right, for the Let me just see over here if I had to open. Yeah, so over here, as you remember, we have that just a second, let me find it for you. Yes, you remember this expression xick. This is the cluster centroid, and we find that distance by calculating the distance between the numerical columns separately and then the categorical columns, and we can assign this gamma value. I'll show you how to do it towards the end. Right now it's 1 by default. So the cost function here is basically the sum of all the dissimilarities, or the distance between each point and its cluster centroid, the sum of it. So if there are 3 clusters, then we get a cost for each of the 3 clusters, and then we add them up to get the total cost for that K prototype algorithm. Okay, so if the cost is very high, then we will say that okay, these number of clusters are not working well, we need to go with some other number of clusters, and then we identify the optimal number of clusters using the elbow method. So it is just like the WCSS, which is within cluster sum of squares thing for k-means, but treating categorical and numerical dissimilarities separately and adding them up, with the option of flexibility by configuring the gamma parameter. So here we have the cost values for all of these, what do we say, 3 to 5 k values, and now we can just visualize this using matplotlib, whatever. So here I can clearly see that there is a sharp elbow at k equals 3. So I can say that I've got 3 optimal clusters in my dataset, and using the elbow method I can conclude that I should probably create 3 clusters in my dataset using the K prototypes and then analyze them. Now, one important thing here, I found the optimal number of clusters using the elbow method. Can I do it through the Silhouette score? The answer is yes, but you need to do some configuration for that. Why? Because if you know about Silhouette score, you remember how we did it in the Gauss distance, right? We got a Gauss matrix, and we just provided a Gauss matrix to the Silhouette scoring method from sklearn, Silhouette scoring class, my bad, from sklearn, and we did it. But in this case, we don't get any matrix by default, and we cannot use only Euclidean scoring for Silhouette score because our dataset also contains categorical columns. So what we would need to do if we wanted to use Silhouette score for getting the optimal number of clusters is we would need to get K prototypes distance matrix, which is pairwise distances between every single data point, and then we can feed that to the Silhouette scoring class from sklearn, and we can get the Silhouette score for each of the different values of K. So that's not required over here, so I just give you the idea of how you can do it. But yeah, here we are using just the elbow method right now. Ping me up, I can create a short clip for that if you want to see it. Okay, because obviously in real world scenarios you always want to use as many validation methods as you can. Okay, so yeah, we can see that we have a significant elbow at k equals 3, so we are clustering with k equals 3, and again we are using the initializing Huang, and then we fit predict, and these we get the cluster labels. Then we assign the cluster labels. We can get that with the labels underscore method of the K proto, which is the object I created. And now I got the data frame with the cluster label for every single data point. Now for better understanding, better visualization, you can see that the age income is a scaled value, which is not really intuitive to understand, so I reverse scaled them, and now I have the original data frame. Loyalty level is pretty understandable, so yeah. Now I'll just show you a little sneak peek into how you can utilize clusters for creating a storyline, and how clusters are basically used in real world, when we are analyzing survey data, when we are analyzing customer data or something like that. Why do we create clusters in the first place? We create it so that we can uh, talk about the data in a better way. We can segment them up and talk about the different segments, the different behaviors of each segment. So I'm just trying to give you a little sneak peek, a little bit of flavor about that. Okay, a little bit of what we say business analysis work. So don't worry, I won't go into the visualization details over here. It's a simple, matplot, a little bit of seaborn and stuff. But let's analyze the visualization and let's see if we can create a storyline using them. Obviously this is a dummy data set, so things look a little bit too perfect, but I mean, we like it because it's easier to understand, right? So here you can see I've created a chart with age in the x-axis and income in the y-axis, and we can clearly see the formation of a segment. Cluster 0 kind of segments the customers which have a sort of a middle age, like between 32, 33 to 42, and who have a mid kind of an income. So this is kind of the mid segment. This is a segment which consists of mid kind of a people who are not very aged, not very young, don't have a lot of income, don't have very less amount of income as per our data set. And then cluster 1, the purple one, is the cluster which includes the young people and they have less amount of income. And then again the black cluster, the cluster 2, includes people with high income and are aged. So you can see that our cluster has made some sense out of our data, and now we can really talk about our data, talk about the different properties of our clusters. Here you can see it's a little too perfect, this particular diagram. Here I'm showing that our clustering algorithm has identified to keep all the people who prefer clothing into one cluster, all the people who prefer electronics in one cluster, and all the people who prefer groceries in one cluster. So that's pretty good, and a little too idealistic. And here I have also shown some cluster distribution that out of our data, 30% have been assigned to 0, to 33.3% have been assigned to 2, like almost one third of our data has been assigned to each cluster. So this is also a part of the analysis. Here you can say that okay, our clusters, so around each person has a 1/3 probability of belonging to each cluster. Then I've also done income distribution. So here we can also see how the income varies for each single cluster using box plots. So I can see that for cluster 0, the income lies in the mid range and the standard deviation is also kind of under control. And for cluster 1, as we saw, it's for the young people with less income, and then this is the aged people with high income. So we can, you see what I'm trying to say is these insights are not very fruitful as of now, but you get the point that we are trying to build a story with these clusters. That is the end point, that is the end value of these clusters. We don't cluster just to showcase our mathematical or machine learning prowess. We do it to make some sense out of our data and to create storylines. So here, as you can see, I can create a small storyline, a small insight from our data set, that there are 3 segments of people in our data set. First segment is a segment of people who are moderately aged, have a moderately high income, and who prefer clothing. Second segment of people are young and they have less income and they are more into electronics. And there is a third cluster which includes the aged people with high income, and what they prefer the most is groceries. For each of these cluster, zero point 0.5 or 50% of every single cluster is male and 50% is female almost. So this is some kind of an insight that you can draw using clusters. So this is very basic, but you get an idea. Now, how can we assign a gamma value to the categorical features? You don't need to do anything over here. You just need to provide a gamma parameter as 2.0. Now, how does it help you do a lot of stuff? Look here. If our gamma is 1 by default, it means that we are kind of providing equal importance to the numerical variables and the categorical variables. But if our gamma is 0.5, then it would mean that we are kind of giving twice importance to the numerical variables as compared to the categorical variables. And if it is 2, then it would mean that we are giving twice importance or twice the amount of weightage to the categorical columns as compared to the numerical columns. And obviously, when we tune the gamma parameter, it would change the cost function's value and things will change, obviously. So you might want to try it. I mean, it's a good option to have if you have a use case, a niche use case, or some kind of a use case where you want to use it, where you have some kind of business understanding to use this hyperparameter. But yeah, cool. This is it kind of about the K prototypes clustering. And as I told you, I'll just show you a little bit of a research paper. I would attach the link to this. This is the one. So this talks about the K prototypes algorithm, and this is a paper called as Huang extensions. I couldn't find the original research paper of Huang. I think it was paid or something. This is also some kind of a snippet, but yeah, you can look at some references over here. I'll attach this link. Okay, so yep, that was it. And thanks for watching, guys, and don't forget to subscribe and like if you like it, and comment it down if you didn't like anything, or if you have any kind of suggestions for me. And thanks for watching. Bye bye.